All right, cool. So, hello everybody. Thanks for joining me again. We are well on our way to proving our main theorem, and today we're going to make our first, I think, big leap in that direction. So, the goal for today is very simple. We're going to prove the weak Mordell-Weil Theorem, which I will refer to as the Mwm Theorem for simplicity. Okay, so recall from last time where we left off. So if we have an abelian scheme over S, then if M in Z is invertible in S, we have that the multiplication by M map, which is going from A to A, is an étale isogeny. Okay, and I mentioned that this is really useful for proving the weak Mordell-Weil theorem. So let me just briefly remind you of what the weak Mordell-Weil theorem says. So it says, given A over K, abelian variety, let's say M in Z bigger than or equal to 1, and we have that K is a global field, then if we take the K points of A, and we mod out by M, then this quotient is finite. So how are we going to go about tackling this theorem? Well, our goal is to use group and étale cohomology. And it's going to be associated to this morphism, which is multiplication by M. So the first key step that we want to look at is a lemma of sorts, which follows almost immediately from what I wrote above in this recall, which is that, under the hypotheses that, A over S is a abelian scheme and M is invertible in S, what we have is that we can look at, how do I want to write it? I'll write it additively. So if we go from 0 to the torsion subscheme of A with respect to M, we go to A, where we're mapping by M. And we go to 0. This is a short exact sequence where, well, it's a short exact sequence, if you like, on, or rather of, so let me write it that way. It's a short exact sequence of étale sheaves of abelian groups on S. So let me explain what I mean by this, in case you aren't familiar with what I mean here. So each of my things here, right, or the M torsion of A and A itself, these are group schemes. And so if we want to interpret them as sheaves on S, particularly, so here, we are working on the étale site, S étale. So this is the I suppose you'd say the small Étale site. That's what I'll choose to go with right now. And so we want to think of these guys as sheaves of abelian groups. So the way that we do that, so we think of A, for example, as a sheaf via H sub A, which is the functor of points, which recall, in our case, this is going to be morphisms of, I suppose, S schemes from stuff to A. So this is able to receive, if you like, Étale S schemes or any Étale cover of an Étale S scheme. And it's going to be contravariant. And you can check that actually the sheaf axioms are satisfied. So the functor of points will provide for us this sheaf interpretation of these group schemes. And so then the claim is that if we make this interpretation, then this sequence we wrote down here is short exact in terms of Étale sheaves on S. And the proof is very simple. I think I'll leave up that thing right there. So what's the idea? Well, really, most of what we want to do is already handled for us. In particular, sorry about the vertigo scrolling up and down. Okay, I think I'll keep it up. So the exactness at the term where we have the M torsion, this is essentially saying, I mean, this is basically equivalent to us having us having an injection of group schemes, right? So this embeds as a closed subgroup scheme of A, and you can check that that implies that you in fact have an injection on the level of Étale sheaves under this functor of points interpretation. And then what you would expect at the middle term, namely that you know, a statement kind of like this. So you want to say that, hold on a second. Okay, let me offer the following interpretation, right? So there are many ways that you can check exactness at the middle term. You could just use the definition, you know, go straight from the definition. You could also think about this via a relationship to group cohomology, right? So I trust that you guys are familiar with the correspondence between the following things. So what do I want to say here? So if hold on a second. Yeah. Okay, so let me offer the following. So assume right now for simplicity that S is spec K. Then if we are trying to do, you know, if we're trying to think about, you know, short exact sequences of Étale sheaves, then we can instead think about things in terms of the underlying K groups. So what I mean by that, and K group is not a good word here, is this, that in general, let's say that you're working with Zariski sheaves, right? Which is perhaps a more familiar situation for a lot of people. Well, a lot of things about sheaves can be checked by looking at stocks. And in the case of Étale sheaves, we can look at not just any old stock, but geometric stocks, which I don't want to precisely define, but the point is that, you know, you will look at, if you like, separably closed fields that map in, and those define for you nice neighborhoods that you study and give you the structure of the sheaf. So if we assume that S is just a single point, well then, what this boils down to is checking exactness on a corresponding short exact sequence, which would be give me all the ks points, where ks is a separable closure of k. And all of our maps are essentially the same thing. We still have multiplication by m. And so then at the middle term, right, what the statement that we want to check is that that am of ks is the kernel of m acting on the ks points of a. And this is very easy to check. So you're basically saying that you can exchange this these operations. Okay. So right. So hopefully that provides a little bit of intuition about what's happening at the middle term. Again, you could just work straight from the definition and think about having Étale covers and so on. But I think this is perfectly fine. So what about exactness at the rightmost term, at this a right here? Well, this, I claim, is basically a direct result of the result from yesterday, which said that, again, multiplication by m defines an Étale isogeny, but more importantly, it's an Étale surjection. So let me uncover that now for general S, right? So there's no reason to restrict in this case. And what we can do is say the following. So to check the Étale surjectivity here, what we need is, we let U be an Étale S scheme. Okay. And then we take alpha to be, something living in the U sections of the sheaf. Okay. And what we want to do is, so we want, if you like, okay, so right, so we have some data. Let me scroll up again. So we have some data involved with sections at this point, and we want to show that M is going to map, or rather we can lift that data via M to data on A. And so a priori, you might have to deal with, general Étale covers and have to think about things a little bit non-trivially. But it turns out that in this case, we can do things very simply. We don't need to think about an Étale cover with more than one map in it. We will only need one map, it turns out. So I'm not going to do that there. I'm just going to do this. So we have our section over U, and again, we're thinking of M as a map from HA to HA. So you should be able to take the definition of this map and interpret what this means. I trust you to do that. And our U prime, which is going to map to U in an Étale manner, it needs to be an Étale surjection, because this will be our Étale cover, will be obtained as follows. So here's U prime. It's going to be induced via, here's U, here's A, and remember, alpha as a section here just defines a map from U to A. So we write it here, and then we have a map from A to A, which is M. So then we take U prime to be our pullback. And what we see immediately is that because M is an Étale surjection, and these properties are preserved by base change, that this map, which, maybe I'll give it a name, I guess I'll call it phi. Maybe I'll call this beta. Phi is an Étale surjection. So this will define an Étale cover with only, one piece in it, which makes things simple. And then what we see is that this M, again, interpreted as a map from HA to HA, sends beta to alpha. That's the gist of the proof. That shows that we have exactness at the rightmost term right here. Okay. Cool. Are there any questions so far? Okay. Well, feel free to interrupt me at any point if you have questions, and I'll do my best to answer. Okay. So with some preliminaries out of the way, we're ready to start tackling the proof of weak Mordelve. So, because I'm going to be doing and saying a lot of things, I'm not going to embed everything in a proof environment, but know that everything we're doing is working towards the proof. Okay. So let me first go back and remember or remind you that we needed some important extra hypothesis here. So we didn't just need that m was an integer greater than or equal to 1 in the proof of the theorem here. So let me change to something you can see. Okay, right? If we're going to use a result like this, well, this required that m was invertible in S, right? And in this case, S is spec K. And so what we need equivalently is that the following. We need that the characteristic of K doesn't divide M. And again, that condition should be clear why we want it from sort of this lemma right here. Okay, cool. So let me do this. All right. So we know as a result of the theorem that we have this short exact sequence here. That should be M. Okay, cool. And again, these are all living over spec K, if you will. All right, cool. So being a short exact sequence, it induces a long exact sequence in a tall cohomology. So, we can, of course, write out what it looks like. So I use the notation here of, hi of whatever the thing is that we're looking at with respect to K. And this indicates two things. So let me write hi here, since I'm going to do this. Okay. So we can think of this in two different ways, right? So one of them is to say that this is hi et al. Of, and then have I flipped this? Hold on a second. Oh yeah, sorry. I have reversed conventional notation. It should be the other way around. Okay, that's fine. Sorry. Okay, so we can think of this on the one hand as the ith et al. Cohomology of this guy as an et al. Sheaf with respect to spec K. So this denotes spec K AM. But we could also think of the underlying gamma module. So let's have gamma, so it's SES. So gamma will be the absolute Galois group of K. And note that the K points of the M torsion, or even the KS points of the M torsion, or equivalently the KS points of A, this thing is a gamma module. Moreover, as a gamma module, we can look at, sorry guys, it's gamma fixed points, and what we recover is just, okay, well, this is the K points. Right, and again, you could replace the M torsion with just A. Okay, so there's an alternative characterization of this, and what this is that it is the ith group cohomology, now of gamma, applied to the KS points. Okay? So one consequence of this result here, that the fixed points just recovers K from the separable closure of K, is that the H0 of K, and I'm just going to write A. Sorry for being a little sloppy, guys. Well, it is just A KS gamma, which is the K points. And that's great because this sort of object here is exactly the sort of thing we want to study for weak Mordelve. All right. So, go ahead. What's up?
What's the upper left cohomology group? What kind of cohomology is that one?
This one?
The one on the left.
Oh, upper left?
Yeah.
Sorry, think of this as a definition.
Oh, okay. Good.
Yeah. So I'm maybe being a little sloppy here, but basically it's a it's a very nice little result actually, that just working over a single point recovers just data relative to the absolute Galois group of the underlying field. Yeah, sorry about that. Yeah, take this as a sort of notational definition. Okay. So, right. Well, what we want to do, of course, is look at the long exact sequence associated to this guy up here. And, we're going to pick up some H0 terms, so we can ignore the H0 term for the M torsion because we don't care about that. But we do care about these guys. So let's start our let's start our long exact sequence at the thing corresponding to this. So, cool. So we have our H0, which again, I've just mentioned is the K points. And then we have it again. And the map that goes between them, well, you can show that this is also multiplication by M. No surprises. Okay. So then there's a transition morphism, and we are mapping to the H1 of KAM. Gosh. Okay, there we go. And this maps to the H1 of KA. And that maps to the H1 of KA. And again, no surprises, the map between them is multiplication by M. Cool. So this is exact as a sequence of groups, particularly the Abelian groups. Okay. So what this tells us is that we get a map from A of K to M. So this injects into H1 KAM, and more generally, we have an exact sequence that looks like A of K mod M goes to H1 KAM, and then to H1, and then the M torsion of the cohomology group itself. Okay, cool. And the map that goes from here to there is, again, given to us by delta, right? We just look at the image of delta, and that's what the image of this guy inside of here looks like. Okay. So in essence, we want to show that delta of A of K, delta of A of K, which again is isomorphic to A of K mod M, is finite. Because that will give our result. And the easiest way to show that it's finite would, of course, be to show that the group that it sits inside of is finite. But it turns out that that is not true, which is a bummer. So let me, I guess, first of all, explain why this isn't the case. So let me think about how I want to say this. Okay, so here's maybe the simplest way, right? So in a few moments, we're going to simplify the problem we're tackling to suppose that the mth roots of unity are contained in K. This has the advantage of, among other things, allowing us to use something called Kummer theory. So let me suppose that mu of m is contained inside of K. Okay. Well then, again, via Kummer theory, what we can say is that h1k of mu m, where again, we can think of mu m as a trivial gamma module, where gamma is the absolute Galois group of K. Okay. This is isomorphic to just a quotient, K cross modulo K cross to the m. But this guy on the right is definitely infinite, essentially because K itself is infinite. So why does this matter? Well, because A of m, or the m torsion of A, is isomorphic to mu m, now thinking of this as a group scheme, raised to a certain power, in this case 2g, for g is dimension of A, which is a result that I outlined in the notes, but I didn't have a chance to say anything about. So in particular, it tells us that h1kam, so this guy right here, is going to be a product of infinite groups, and so it's infinite. So we need to be a little bit more clever to understand what the image is. We can't just look at this guy itself. And so the way we go about building that group is by looking at certain ramification conditions and spreading out. So let me start with the spreading out, which may not be familiar to people. Okay. So a priori, we have this guy here, A mapping to spec K, right? And it has a bunch of nice properties because it's an abelian variety. You know, it's geometrically connected, it's smooth, it's proper, and it defines, you know, there's a group scheme structure on A. Okay. Well, what we want to do is work over a slightly nicer base, because that will allow us to, well, so I mentioned that we're going to want to think about certain ramification conditions to cut down a suitable subgroup of this guy. And the way that we get at that, we're going to need a little bit more data to play with, essentially. So what we can do is this. We can take our guy here, and we can spread him out. How do we spread him out? Well, we get, let me try to make that look a little bit more visually distinct. Okay, hopefully that looks different enough. This is going to map down to some guy u. What is u going to be? Well, u is going to be spec of OKS. Now, I'll talk about how this guy arises in a second, but I want to first remind everybody what I mean by this, because this is notation that's common in number theory. Okay. So OKS sits inside of K. It's the subring, and in fact, it defines a Dedekind domain, but it's the subring of S units. And how is that defined? Well, there are a couple of ways that you could define it. I'm going to do it this way. So S here sits inside of what are called the places of K, which I denote by capital sigma sub K. So let me not do this so backwards. So I'm going to oh, that's janky. What the heck? Huh. I didn't know they had a weird select tool like that. All right. It doesn't matter. Okay. So S in here is a finite set of places. What are places? If you're not familiar, then I think like it's fine today. Tomorrow you'll probably want to review for tomorrow because it'll matter more. But basically what places correspond to are two different things relative to a global field like K. One is that they correspond to what are called finite places or sometimes finite primes. These are basically, so it's a finite set of places. So places are either finite, and so correspond to prime ideals of a suitable ring. What ring is that? Well, if K is a number field, where this is a little bit simpler to talk about, then that ring is just the ring of integers. If you're talking about K being a global function field, there is no ring of integers. So you have to be a little bit more careful, but know that this guy here of S units, which I'll define in a second, definitely is one such thing. So they're either finite or they're infinite, in which case they correspond to embeddings. So for a number field, these would be complex embeddings of your number field. So you have some injective ring homomorphism from K into the complex numbers. So this is the, I guess, prime interpretation. And then there's the absolute value interpretation where they are they are absolute values. So they satisfy those axioms. So that's a little bit of a primer. Hopefully it's not too redundant for people. But basically, if we select some finite set of places, typically it will contain the Archimedean places. In fact, it should. So finite set of places with the Archimedean ones, so that would be the infinite guys. Then what we say to ourselves is that it is this. So give me all the A and K such that what? Well, such that the valuation, so this is related to the prime ideal interpretation, essentially. If we eliminate all the infinite guys, then this makes sense. So we want it to be non-negative for every V not in S. So that's what the S units is. Turns out this is a Dedekind domain, which is great. And it has a lot of nice structure. So OKS, so the S units, which would be the units of this guy, is finitely generated as an abelian group. And the S class group, which is the Picard group of the S units, this is finite. Okay. If you are confused about this rather rushed, botched definition and recollection of places, then please ask me closer to the end of this, and we can have an involved discussion about it. Okay. Other than that, let me talk about the spreading out here, right? So let me just move this down. Whoa. Oh, sorry. Let me move this down. Oh, this is so strange. All right. We're just gonna draw it from scratch. I'll have to figure out how I should go about that in the future. Okay, sorry. So Right. I'll call it U for simplicity. So again, S is going to be contained inside of the finite places. Sorry, the places finite containing all infinite places. And what conditions do we want? Well, first and foremost, we want A to U to be an abelian scheme. Okay. What else do we want? Well, let me think here. We want M to be an S unit. So it should be in and we want that the size of the M torsion of A, so let me say it this way. So take the M torsion, take the underlying set or underlying topological space, give me its cardinality. We want this to also be an S unit. And the reasons for this will become apparent in just a second. Okay, so how do we get this to happen? Well, I don't want to go into too much detail. I give references in the notes if you're curious about how this works, but basically, in order to get this kind of result, right, it's certainly easy to define a variety over U for some S. And really the way that spreading out works in a simple context is that maybe a priori everything is, let's work with Q. Maybe a priori everything's defined over Q, all of your equations. But if you have finitely many equations, well, then there are only going to be finitely many denominators. And so you don't actually need to consider all possible denominators. You only need to consider some subset of them, some finite subset of them. And the same idea applies here. These S units, S here is sort of mediating what we're allowing to appear as denominators. So we can arrange that that we only have to care about certain denominators, and then you just need to take some care to make sure that the key properties of this morphism are preserved, like the smoothness, the properness, and some of that's maybe a little non-trivial to do, and some of that's a little bit easier. But I leave it to the notes to maybe talk a little bit more about that. As far as the other two conditions go, about having M be an S unit and about having this thing be an S unit, really that's a matter of you get this guy first so that it's an abelian scheme, and then it turns out that enlarging S is pretty much harmless. So we basically just suitably enlarge S so that these conditions are satisfied. So you say, all right, what do these things look like relative to the ring of S integers, and then you throw in, you think about the relationship of these things to K, and you say what kind of denominators and so on are appearing, and then you just throw in the suitable data to S. Okay. So why does this matter? Well, from a classical perspective, so if you've done maybe a little bit more traditional number theory, what this is doing for us in a sort of slick way that will allow us to use Étale cohomology is that we're accounting for badness, if you will, right? So in particular, by having these three conditions, we are eliminating primes of bad reduction for our abelian variety A. So we're taking S to basically consume those. And we're doing a little bit more, but that's maybe how you should think about this. So, in general, if you study elliptic curves, then they'll be oftentimes badly behaved at certain points, and we want to avoid that. So that's essentially what we are doing here. Okay. Try not to shift this around too much. Cool. Okay. So what we can do, first of all, is note the following. That you can show without too much difficulty that both the k points of A and the k points of A mod M may be identified with corresponding data for this script A associated to U. Like so. Okay. Which means that we can study instead of studying delta of A of K, or rather because we want to get delta of A of K, we can look at the associated map relative to script A of U. Okay. So again, we have an analogous short exact sequence, which goes from script A, M torsion, to script A, to script A. And again, this is multiplication by M to 0. And yesterday I said, this is why we basically needed this result to hold for general schemes as our base. It's because we wanted to think about this guy here. So this is going to be also short exact. So it's going to induce long exact sequence, and in particular, it will induce, just as before, the analog of our delta map, right? So, delta, recall, was this thing that was mapping, well, you can take it to be mapping A of K mod M to H1 K to the M torsion of A. So if we reinterpret all of this in this language, right? Well, now we have A of U mod M injecting into, and then now it's going to be the first Untitled cohomology of U applied to script A M. Okay. And moreover, there is a commutative diagram that all this data fits into, which is that, so I'll say that we have A of K mod M down here. These things we identify, and then this similarly is mapping into H1 of KAM, and then thinking of this as also an Untitled cohomology group with respect to spec K, then we get a map like this. Okay, cool. So what this means at the end of the day is that, again, we want to study the image of this map right here. Okay, so then this is where the promised ramification conditions enter the picture. So before I talk about that, I want to pause. Are there any questions? Okay. There's something that I'd like to note about this sort of identification procedure, in case you're skeptical. Recall that U is coming from a Dedekind domain, so this is a Dedekind scheme. And it turns out that Dedekind schemes, or Dedekind bases, really, satisfy a lot of nice valuative criteria. And so you're going to use those valuative criteria right here for this kind of correspondence. So I'll say that, and then I'll leave it at that. Okay. So we're interested in that image. Okay. So let's talk a bit about ramification conditions. So let's take little u in big U to be a closed point. Okay, what does this mean? Well, equivalently, it is a non-zero prime ideal of the ring of S integers. Okay, we get an inertia group. So there is an inertia group which I'll denote I sub u, defined in one of several ways. Oh, shoot. So what's the first approach? So I'll say approach 1. So recall that we had gamma was our absolute Galois group. Ks over K. Cool. Okay. Well, associated to U, right, what can we do? Well, we can complete K, right? So U induces K sub U, which is going to be a local field. And that has an associated absolute Galois group, which I'll say is gamma sub K sub U, which is absolute Galois group of, then you take this guy and its separable closure, and you map, and you look at this. Okay, so then we want to use this group to think about IU. So how can we do that? Well, here's how we can do it. The inertia group sits inside of gamma KU, which sits inside of gamma, again, by taking hold on a second. Let me not get ahead of myself. Okay, so let me just handle this for now. Via what? So we again take the separable closure to be the over field, and then the base field, instead of being KU, will be its maximal unramified extension. If you're not familiar with it, it will come up in a second what it is, so don't worry. Okay, so that's IU, which clearly sits inside of gamma KU. Okay, but what's the relationship of the absolute Galois group of KU to the absolute Galois group of K? Well, what we can do is we can take, so I don't need the K there, via sigma, which is defined, again, on the separable closure of KU, we have this diamond, right? So there's KU separable closure, there's the K separable closure, there's the completion at U, and then there's K. Like this. So then what we can do is we can restrict our automorphism of the separable closure of the completion at U to the separable closure of K. And what we have is that this will define for us an element of gamma. So it will fix K, because again, sigma fixes the completion of K at U. Okay. So this map is an injection, as you can check. Let me think about that. Is that true? I think this is true, and I think you can work with a uniformizer. But don't quote me on that. I think that's the case, though. So what this should allow us to do is identify the inertia group as a subgroup of the absolute Galois group, as such. Okay. So that's one sort of classically Galois theoretic way to think about the inertia group. And then there's a second, more geometric, I'd say, way to think about it, which is this. So allow me to think for a second. Yes, okay. So associated to little u, right, we have our stock of our structure sheaf at that point, okay? So this guy is, of course, a local ring, and as a local ring, it has something called a strict tensilization. So let's say UU, strict tensilization. What is the strict tensilization? Well, again, there are a lot of things that could be said about it, but let me say this. So it's, for one, strictly Henselian, no surprises. So what does this mean? Well, the Henselian part is easy. So a ring is, and really this is a condition on local rings. So local ring is Henselian if it satisfies the conclusion of Hensel's lemma. If you're not familiar with Hensel's lemma, know that it is a result about, really the key example you should have in your mind is you want to think about mod p data and say mod p squared, mod p cubed data, and so on. And then you want to think about p-adic data. And the claim is that, what do I want to say here? Yeah, the point is that you can essentially lift roots, mod p, to p-adic roots. That's oversimplifying things, but that's the gist of it. And so everything should be done with respect to, you want to quotient out by your unique maximal ideal and look at things there. So that's what Hensel's lemma is about. It's a lifting result that allows you to solve equations in a simple context, which is, modulo some finite prime, and then get data in a more complicated context. Okay. So it being strictly Henselian is essentially, what to say? Hold on. Well, so, okay, let me say this. So it's a local ring. With a maximal ideal M OUU, where the M here is actually the maximal ideal of this guy, the stock of the structure sheaf at U. So this is something that has to be proved based on a construction or yeah, you have to give a construction, then you can prove this if you like. And more importantly, it has a quotient. So S again denotes separable closure. And what's kappa here? Kappa is the residue field of U at U, which means that it is take the stock and mod out by M. Okay, so the point is that we recover the separable closure of this guy. And this will be important in a second. Okay, so then how do we get the inertia group from this data? Well, let me think for a second here. Yeah, Okay, so here's what we do. So we say that, okay, OUU is strictly Henselian. It has a fraction field, right? So this is going to be some field. And then this guy, which maybe I'll write as F sub little u, just for simplicity, has, you know, an associated yeah. It has an associated absolute Galois group. Okay, and let this be I sub u. All right. So I've said a lot of words. I wrote down a bunch of things. Let me explain what's going on, right? So the first thing I want to say about strict tensilization, like why should we care about this kind of construction? And the point of it is that if you take spec of a strictly Henselian ring, then what you find is that every finite étale cover of that guy is split. And so spec of a strictly Henselian ring is étale cohomologically trivial, right? So what you want to say then is that like this is the this is like the basic open neighborhood of a point in the étale cohomology, right? If you're doing let's say singular cohomology, then you know you have Euclidean topology and basic open neighborhoods are very easy to get to. But in algebraic geometry, and particularly when you're working with étale cohomology, your neighborhoods can be more complicated. And so this guy provides a nice basic neighborhood, essentially. Okay, so that's one reason to care. You know, because what IU is measuring is, well, it's controlling local data of the point for sure. And in particular, it wants to know about, well, I'm getting ahead of myself. I'll explain in a second.
Hey,
okay.
Zach,
Yeah, what's up?
how come you can replace that ring OUU by its strict tensilization and still say that it's an open neighborhood of the same point? Like, how is that consistent with the geometry of the object?
I'm sorry, so you're saying that if I take like spec of the strict tensilization of the structure sheaf at U,
Yeah,
sorry, the socket U, like how is that
still a neighborhood of the same point.
how is that still neighborhood of the point? Yeah, let me think for a second. That's maybe not quite the right way to say it. Hold on.
We can talk about it later too if you want.
Yeah, I mean one way to think about this is that really you want your basic open neighborhood to be contractible, right? And from the perspective of the étale fundamental group, then this guy is going to be contractible, again, because all of its étale covers will be split. So yeah, we can talk about that more, but that's maybe a more precise notion. Actually, that's a better notion of which it is a sort of basic open neighborhood, because it has that contractibility.
That makes sense.
Yeah, and like, if you're working on the level of étale cohomology, that's what will matter anyway. You know, in this case, it will be trivial cohomologically, and that's going to be important. Okay.
Thanks.
Yeah, no problem. Okay. So it's maybe, oh, hold on. There we go. So it's maybe not immediately apparent why these two approaches are related to each other. So let me offer just a brief explanation of how they are related to indicate that these different ways of viewing this thing are in fact the same. Here we have the maximal unramified extension of this complete field, right? So the way that this is obtained is by essentially adjoining a bunch of appropriate roots of unity, right? So you think about, you know, whatever this place is, or this closed point U, maybe the best way to do this is with an example. Do I want to get into that? Yeah, so let me put it this way. Okay, I'll put it this way. So this guy is most definitely obtained as a filtered colimit of all of the finite unramified extensions of this field, right? Because, you know, the compositum of two unramified fields is going to be unramified, and so you just go over all the finite extensions, you get this guy. Okay, so nothing crazy there. All right, so let me write that. So okay. So then what about the strict tensilization? So the strict tensilization is, well, it turns out that it is again, a filtered colimit of finite étale algebras. So when we take frac of it, then we can now think of a filtered colimit of finite étale f sub u algebras, or not f sub u, frac of ou sub u algebras. What am I even saying? Oh, I'm silly. Okay, sorry. And we'll take a break here in a second too, just to give everybody a chance to breathe. But yeah, so here we have that this guy is a filtered colimit of finite étale OUU algebras. You take frac, you get a filtered colimit of finite étale, and then you'd like to say, you know, frac of OUU, but in fact, what that is that's just K sub U. So that'll be a filtered colimit of finite étale KU algebras. And so then it's very easy to pass from the finite étale KU algebras to just the finite unramified extensions of that guy. So what you see is that the underlying fields, right, used to define both Galois groups are the same. And so then you get that both approaches recover for you the same notion. And that's useful because the second notion is very good for étale cohomology computations. And the first approach is very good for traditional algebraic number theory type arguments, where we argue about ramification the way that you would in, say, a first course on the subject. So, you know, this relates maybe more geometric and more algebraic, although I guess ramification is already a very geometric notion. So it relates to two notions. Okay, let's take a break and resume at 11:15, where I will use the machinery we've developed so far to really get into the meat of the proof, and then that'll be it for today. So yeah, and again, please ask me any questions you have.
Hey, Zach?
Yeah.
During the break, I was thinking, so you said ramification is geometric in nature?
Yes.
So the way I understand or have heard of ramification is something about like a prime in like splitting, an ideal splitting into primes of power higher than one in some like number field ring of integers or something.
Mm-hmm.
So could you just say a word about like the geometric?
Yeah, sure. Okay. Yeah, let's do that. I'll do that in red. I think it's tradition to do this in red, so. Okay. Yeah, so let's just take that example, right? So I'll take my favorite example of this phenomenon happening, which is also one of the simplest, right? So we have Q adjoin I and Q, right? The corresponding rings of integers are Z adjoin I and Z. So then there are three different kinds of splitting behavior, right? So P is 2, then what you have is that 2 where 1 plus I here is the ideal cutout in Z adjoin I. So then if P is 3 mod 4, then P is inert. And if P is so really this should be, I'm being very sloppy here. So P will be like Q1, Q2 for conjugate prime ideals, right? So if we think about instead of just these guys spec, right? So Z includes into Z adjoin I, and so that means that there's a corresponding map from spec Z adjoin I to spec Z. And what we're doing is we're thinking about the fibers of this map, right? So the fiber above 2, so maybe I'll call this map pi. So then pi of 2 is a single point. Pi of 3 is 3, to be a bit abusive with notation. And pi of 5, let's say, is okay. So right. So what we see here is that ramification occurred for 2, right?
Yeah.
And the fiber above that point has a single point in it. But that point sort of has multiplicity 2 here. For 3, it was inert. And, well, we recovered only a single point. That's exactly what it means. And for here, we had splitting, and we got distinct points, right? So one way you can think about this is that spec Z adjoin I mapping to spec Z should be some kind of covering map. In particular, it should be a double cover. And that can be made precise so that even at the inert points, you know, this is still a double covering type phenomenon that's happening. One way to see that is if you complete at the corresponding primes, right? If you complete at 3, then, sorry, not complete. If you take the residue field at 3, then what you obtain is F3. And if you take the residue field at 3, you obtain F9, which indicates that there is a kind of double covering phenomenon going on. But the obstruction to this being a double cover is provided precisely at this ramified point, right? Because there we don't have an honest double cover. And so what we can say is that this map is actually a ramified double cover, and it's ramified at the point 2 in a sort of geometric sense, right? Here we're thinking about ramification similar to how you think about ramified covers of like Riemann surfaces. And so then it turns out that, you know, this simple analogy actually goes way deeper. You know, you can generalize Galois theory so that, you know, Galois theory and covering space theory are basically on equal footing. And the Attell fundamental group sort of takes this one step further, and that relates to the fundamental group itself of, you know, say a complex manifold or something. Does that answer your question?
Yeah, that's great. Thanks.
Okay, yeah. And then of course, like, you know, if you don't want to think about any of that, then you could also just look at this algebra geometrically and say, oh, okay, well, let's think about this map as you know, as a morphism of schemes, and then let's study this guy pi, and you know, in algebraic geometry, there's a notion of ramification as well, and it turns out that the two coincide when they both make sense. But yeah, okay. So where are we? Okay, so we've come through with several ways of thinking about the inertia group, which we will now put to great use. That is our goal. So yeah, so remember that our goal was to track delta of A of K. And so the claim that I want to make is that delta of A of K lands in what? Well, it should be the subgroup of squiggly thing, which I know is not how you're supposed to draw psi, but it's okay. So we want to look at cohomology classes. And the claim is that it consists of cohomology classes that are unramified outside S. What does that mean? So that means that if we restrict to the inertia group, then we get 0. And this is for every closed point, U and U. Where, again, this restriction, right, we thought of, this could be said as group cohomology with gamma as our group, and IU is a subgroup, and so this is taking place, so this guy lives in H1 IU AM. Okay. So having this condition be the case, this is a condition for cohomology classes to be unramified. Okay. So why is this true? Well, one way is to note that, again, we can study our souped up version, right, where we embed the quotient here into our first Étale cohomology of this guy. But this restricts down to this, as mentioned before. And in turn, we can restrict to, well, this. Okay? So if we interpret IU, the inertia group, in the second way, right, as the absolute Galois group of F sub U, then what that precisely says is that this composition factors through this guy. So it should factor through H1 Étale of getting ahead of myself. But as we mentioned, this guy is Étale cohomologically trivial. So, right. So let me maybe phrase this in a little bit more concrete terms, if this seems a bit weird. So given a closed point, so we want to know if, so we want to know if the restriction of, let's say, some squiggly A cohomology class like this, you know, again, induced by or given as the image of some A living in quotient. We want to know if the restriction of this guy to that. Sorry, I'm getting ahead of myself, guys. Okay. This is straight up what we're trying to prove. Okay. No, hopefully no confusion there. You should think of this guy living in here as an obstruction to M divisibility, right? And so what that means is that, so psi A should be viewed as an obstruction to M divisibility, just as A itself is. And so, I want to keep that on screen. A itself, should be viewed as an obstruction I don't know why I'm putting square brackets around M. It's not really necessary, but oh my goodness. Sorry, guys. This word has too many I's in it. Okay. We want to view this as an obstruction to M divisibility, but not any longer as an element of that quotient, but as an element of this, okay, F sub U mod M. This is if we are looking at this guy restricted to this IU data, to the inertia group data. Okay. So in other words, we want to know if M, viewed now as a map from F sub U, the F sub U points of A to the F sub U points of A, is surjective. And the way that we do this is, well, we note that, again, by a sort of valuative argument, the FU points of A can be identified with the, I guess, OUU strict tensilization points of script A. And then using that this guy is Attell cohomologically split as before, or rather that every finite Attell cover is split. So if we think about this argument here and this argument here, all that we are really doing is concretely tracking what's happening as we move from these cohomology groups, from one cohomology group to the next. And then the fact that this factors through here is precisely this bit down here. So I know that's a little weird. And certainly I find it a bit odd myself. But this is one reason why we want to consider ramification, is because it'll turn out that the, let's scroll up, right? It'll turn out that this subgroup with these ramification conditions on it is finite, which is good. Okay, cool. So then something else that I want to note.
Hey, Zach, there was a question in the chat. Did you see that?
I did not know. What's the question?
Yeah, so somebody basically asked, I guess they're having trouble following a little bit, like sort of where the argument's going, kind of like lost the forest for the trees a little bit, and just could you give a high level like sort of overview of like where's the argument going and stuff. And also there was actually a specified point here. Why should you expect that a tail cohomology should be helpful in proving the weak Mordell-Weil theorem?
Metal cohomology.
NV. Yes. Okay. Yes. So let me do that. I apologize for losing people a bit. All right. So let's get back to our roots, right? What we're trying to do. So our goal is to prove this, right? So naturally, this quotient is going to be on our minds. And where does this quotient come from? Well, this guy A of k, right, is related to the ks points, so the separable closure points, via taking fixed points, right? So where you're thinking about the absolute Galois group. So it's already something that would not be all that unexpected, that you should be looking at group cohomology. And the fact that you want to deal with the quotient by m, well, since we understand something about the m torsion of this guy, and we know that there's a short exact sequence that involves m and the m torsion, which will recover what we're looking at on the level of cohomology, that's why it makes sense to look at, let's say, group cohomology. So why should we care about étale cohomology in this case? Well, the reason why we care about étale cohomology is because we want to deal with a slightly more complicated base, right? I mentioned that in the classical case, you have to worry about primes of bad reduction, and there isn't a nice like purely group theoretic way to deal with the primes of bad reduction. So by appealing to étale cohomology and spreading out my abelian variety to an abelian scheme, then I can deal with some of those difficulties in a nice way. So that's a reason to pass to étale cohomologies, because it makes it easier to deal with some of the pathologies that pop up in practice. So then basically what remains once right. So hopefully that justifies why we care about cohomology. And then remember that I said that the quotient that we care about, the k points mod m, lands inside of a first cohomology group. And that first cohomology group is infinite. So we're going to need to somehow wrap our hands around the image. We can't just deal with that cohomology group itself, because the cohomology group is just too big. So the purpose of looking at ramification is to actually understand what group we fall into, what subgroup we fall into that's finite. So where this proof is going is that I want to show that that subgroup is finite. So this subgroup here with the unramifiedness condition, we want to show that that is finite, and then that will prove that the quotient itself is finite. Hopefully that makes sense. So what I'm attempting to do right now is sort of work away the geometry so that everything is just purely algebraic. And then I will prove a simple statement about just gamma modules, or, about gamma modules. And I'll use group cohomology to sort of finish it off. Does that help? Does that answer the question? Let me click on chat. Okay. Yeah, sorry. I really ought to have stressed this a little bit more at the beginning. I'm sorry about that. Okay. Cool. So really, before we get to just the simple verification itself, there's only one other thing we need to note, and I'm not going to prove this. The proof is not difficult, but not very enlightening either, and not terribly important. so if we look at the KS points of AM, so maybe I'll say note or fact or something like that, this group is unramified outside S. I realize that the notation, this phrase is a little overloaded, I'm sorry. So in the sense that the inertia group acts trivially on this thing for every close point. Okay, so again, this is a gamma module, so it emits an action by gamma. And IU we identified as a subgroup, so IU acts on it as well. And then the unramifiedness outside of S is saying that to the close points of U, which again, this is U is closely tied to S, we have a trivial action. And this is maybe not so foreign if you are familiar with algebraic number theory, where ramification behavior can be viewed in terms of a simpler notion of inertia group and its action. But I won't get into that. I'll just say that for here. All right. So what all this means is that we can prove a sort of, I guess, affine version of the problem now, where we only need to work with group cohomology. So let me say that. So here's our finishing touch, if you will. So again, we have, just to remind everybody of the setup, we have a global field with an absolute Galois group, gamma. We have S inside of the places of K, finite, containing the infinite places. And then we have M, which is going to play the role of it's going to play the role of the KS points of the M torsion of A. Okay, so this is going to be a finite, discrete. I'll say what discrete means in a second. Gamma module. Oh, found a typo in my notes. It's fine. Such that M, which is the size of M, is an S unit. And M is unramified outside S. Okay, let me just say what's going on. So M here again is this guy here. This is our finite discrete gamma module, and all the conditions that we looked at. So this unramifiedness condition is captured here. The fact that M here is an S unit is what we did. We said that when we spread stuff out. And the other information is here too. And I'll put in the unramifiedness stuff in a second. But saying that M is a discrete gamma module, really what you should think about for that is that the discretes may be a little redundant because it's finite, but discrete gamma modules are just the kind of gamma modules for which we can do group cohomology. Because, and again, I'm not going to get into the details here, but gamma is an infinite group. It's a topological group. And so doing group cohomology with gamma requires a little bit more care. And you can't just take any gamma module and recover a nice notion of cohomology. So discrete here is just saying that group cohomology can be taken for M. Okay. So then the unramifiedness set, which I'll define, is going to be finite. So what does it look like? Well, it's this guy, H1S of Km, which is defined to be, give me the cohomology classes in the first cohomology here, such that the class is unramified outside S. This claim is that this group is finite. And if you'll note, this group right here is the same group that we entertained in this claim, right? Viewed in our new language. Okay. Wow, not like that. Okay, cool. So let me leave up the result and get to the proof. Okay, cool. So let me try to signpost this argument as well as I can, so that nobody gets lost. So I'm going to reduce to the case where M is something very simple. So we want to reduce to the case M is mu sub M. We want to have mu sub M be contained inside of K. Again, this is a Kummer theory type condition. And we want to have that the places of K associated to M, right? Because we can factor M being some integer, are contained in S. Ooh. Why do we want these conditions? Well, the reason why we want these conditions is because the result is going to be very easy to show in this case. Particularly, why one might think about these particular things is that we're going to show that there's a short exact sequence that pops up here, which is useful to think about. Namely, one mapping to the quotient of the S units by nth powers, mapping to and then mapping to the card group of the S units, M torsion. So again, I will construct this short exact sequence, or sorry, it's not short exact. I will construct this exact sequence in a second. But buying into the existence of such a thing, then what we can say is that this guy, which we want to show is finite, is sandwiched between this, which is finite because the S unit theorem says this is a finitely generated group, and this thing is full rank, so the quotient's torsion, hence finite. And this thing is finite by the S class group theorem. Okay, so that's one reason why we want to make this simplification, is because we get a sequence like this. And, why can we make these reductions? Well, first and foremost, let me think here. Okay, So the easiest one to arrange for is that the places of K associated to M are contained in S. Why? Because all that has to happen for that is that we enlarge S, and when we enlarge S, then this group can only get bigger. And so if this group gets bigger and we show the bigger group is finite, well, then definitely the smaller group is finite. So this assumption is harmless. Okay, the assumption that the mth roots of unity are contained inside of K follows along similar lines. It involves a little bit of Galois theory, not a lot. But I don't think it's terribly important. Again, ask me later if you want to know, but we can also make this assumption without too much hassle. So then it remains to show that we can make this assumption that that M is mu sub M, the mth roots of unity. So let's try to tackle that. And let me give this sequence a name because it's going to appear again. I'll call it star. Okay, cool. So what are we trying to do? Yeah, just a second. Okay. So the first reduction we want to make is this. So okay. So first of all, we can enlarge K. To some finite extension. Oh my goodness. Big K, such that its absolute Galois group acting on M is trivial. Yeah, let me think. Yeah, okay. All right. Sorry, guys. I realize I'm trailing a little bit. Okay. So again, we're trying to reduce the case that M is mth roots of unity. Okay. So that is a group on which the absolute Galois group gamma acts trivially. So what we want to arrange for is that gamma acts trivially on M, and then we can basically split things, right? Because then we can say, okay, M's a finite abelian group. It breaks up as a product of finite, abelian groups. Rather, each of them, it'll break up as a product of mu's, basically, of roots of unity. And so then we can simplify everything that way. So we'd like to make this step. So how do we do this? Well, if we take this extension, what can we do? Well, first of all, extend the places of S in sigma k to places of sigma big K. Obtaining S sub big K. Okay, so this is literally about lifting places, which is something that if you've taken algebraic number theory, you're familiar with. If not, then we can talk later. So then there is an inflation restriction sequence. What does it look like? Well, the way that every inflation restriction sequence plays out is sort of like this. So and then this is, oh wait, sorry. Okay, where this is inflation and this is restriction. This is exact. Okay, so what's going on? So this guy here is referring to the Galois group of Ks over K. This here is referring to the Galois group of Ks over big K. And if you remember your Galois theory, then the relationship of these three groups is that this guy sits inside of this guy as a subgroup, and it sits in there as a normal subgroup. The quotient is this thing here. And so this map via inflation is basically a map from a group mod a normal subgroup to the group itself. This is the cohomology map induced by the quotient map from G mapping to G mod N. And then this map is, again, the cohomology map induced by the inclusion from this, from a subgroup into a group. And the fact that this defines an exact sequence can be viewed in a lot of different ways. Maybe one highbrow way is to say that you have degeneration of the Linden-Hochschild-Serre spectral sequence. Or you could just do direct computations and show that it is exact. But know that we have an exact sequence like this, where these maps are given actually quite simply. It's easy to write down a precise definition of what they are that's not too terrible. Okay. So we get this inflation restriction sequence. And moreover, what we can say is that restriction maps the ramification associated to this guy into the ramification, not res, into the ramification associated with this guy. Whoa, hold on. Why did it do that? Weird. Okay. So restriction is going to map the ramification data that we want to track into the ramification data here. I'm not going to go into this. I encourage you to deduce this on your own. I will say that this is where the hypothesis that M is unramified outside S becomes very important because it gives this to us. Okay, so why should this sort of thing matter? Well, because this guy on the left is finite, right? And that means that this ramification, the one that we want to study, is going to be finite if the bigger ramification, if you will, is also finite. So what this means is that we can actually assume that the action of gamma on M is trivial because we can replace little k by big K and big gamma by big gamma sub K. Okay? So then all that's left, right, for the simplification. So we can use the, I guess, the Abelian group decomposition It's a product of a bunch of cyclic groups, right? So they can all be written this way. Again, because the assumption is that M is a unit here. So in fact, all these roots of unity groups will be cyclic of the appropriate order. This abelian group decomposition is an isomorphism not of only abelian groups, but because there's a trivial gamma action on both sides, so this is an isomorphism of gamma modules. Okay. And so then what that says is that if we want to study the H1 of M, then we are studying the H1 of a product of things, which splits up as a product of H1s of these guys. And so if we know each of them is finite, then the thing we want to study is also finite. So this is the simplification. Are there any questions about that? Okay, cool. So now recall that we have, and we're on the finishing stretch, guys, so don't worry. So recall that we have this sequence here that I claimed, this guy fits into, giving us finiteness. So in order to construct this, this sequence, there are a variety of things that we need to worry about, ramification related stuff and so on. I'm actually sort of debating now that I look at it. It seems like there's a lot here. Okay, I tell you what. I think everybody has probably had enough for today, and this is a good thematic stopping point because we're now at, we've completed the simplification, and all that's left to do is do some number theory, essentially. So I think what makes the most sense is to leave it here for today, and then for tomorrow, we will show that we have this sequence here, and then we will finish things off by talking about height theory and proving the Mordell-Weil theorem. So yeah, I think I'll leave it at that for today, and please ask any questions you have.